Good morning, Griffins. All right, it's time for the AP Physics lecture on curved roads, and this is where the circular motion part of Chapter 6 comes into play. So I'd like to draw an off-ramp from a freeway as seen from above. So it's a curved road. It goes around the arc of a circle, and this is just part of the road I drew, just a segment of it. And we're going to give this curve a radius of curvature of about 50 meters. That means that when they drew the road, they put a stake in the ground, 50-meter long piece of string, and they staked out where the road was going to be. And then they started moving earth to put in this road. Now, on this road is going to be a car, and this is the top view of the car. Give it some wheels. And the car is going to be driving this way. What I'd like to know is what's the fastest velocity that that car can drive before it slides out? Now, in order to solve this problem, we have to beat two things against each other. And for that, maybe we should draw a picture of the car as seen from behind. So there's a couple of tires, some sort of structure to the car and some glass top thing here, okay? And the car is driving into the page and it's turning to the right. And so a free body diagram for the car would show us that the car has some weight. So the car has a mass and multiplied by the acceleration due to gravity. And then road is going to provide a normal force. And if this car is going to turn in a circle, one thing we know is that we need a centripetal force. And that centripetal force is going to be provided by friction. And in this case, it's static friction. I know that's hard to think about because the wheels are rolling, but each wheel is momentarily in contact with the ground, and it's not moving side to side. It's only moving forward and back. So in the transverse direction, this is static friction that holds your car on the road. And in fact, this is the maximum static friction we need if we want the maximum velocity. So this is an unbalanced force, and that means the car is going to accelerate to the right, but it's accelerating to the right in such a way as to produce circular motion. And we happen to know that that exact acceleration necessary to go in a circle is equal to v squared over r. That means that the centripetal force necessary to go in a circle is mv squared over r. It looks like I'm going to have to retire this pen. Let's have a little ceremony. There you go. That was fast. So to finish solving this problem, we need F max to be equal to mv squared over r. F max, however, is mu s times the normal. And the normal, according to this diagram, is m times g. And the m's cancel. So we can move the r to the other side, and we get mu s g r equals v squared, or our velocity is going to be the square root of mu s times g times r. Now, one thing I didn't tell you is what mu was, and let's come up with just an average value for rubber tires on a concrete road. Let's say that mu s equals 1. I know I said that it's a little more than 1, but just going with the low end estimate. So the velocity you can carry in this corner is going to be 1 times 10 times 50, or the square root of 50. Which, oh yeah, I'm going to bring this calculator. Well, we know the square root of 49 is 7, so really this is going to be really close to 7. Square root of 50, 7.07. So you can do 7 meters per second. That's a pretty slow velocity. 7 meters per second, it's a running speed for a person. So you really have to slow down. Now, why is it that when we take a freeway off-ramp, we tend to be able to go much faster? Well, I've probably underestimated this. And maybe this is a little small for a road. Maybe it's a very tight corner. But there is something that we do to roads that allows us to go a little faster. And that is that we banked the roads. A banked corner. A banked corner has the same appearance from the top. But from the side, the road is tilted by an angle theta. And then I'll draw my little car going into the page. Now the free body diagram is a little different. Now the normal force is this way, weight is this way, and friction, well, friction is still parallel to the roadway, so friction would be this way if necessary. I'm putting F max for the maximum amount of friction. See how fast you can go. Before we do this, I'm going to do a slightly different problem that's a little easier. One of the things that people don't know about banked corners is there is a speed that you can drive on a banked corner for which you don't need friction to go around the corner, where the small component of the normal force that's pointing towards the center, and yes, this is a very weird thing. We are not going to tilt the coordinate system because we need a centripetal force, one that's towards the center. So I was told this by a race car driver, that you can drive a race car at a speed, and it's usually not as fast as you're going to be racing, and you can take your hands off the wheel and the bank of the road will push the car around. And he said that you need to know what that speed is, because if you're going faster than that speed, you actually have to turn in the direction of the corner as you normally would. But if you're going slower than that speed, to prevent your car from going into the infield, which may have a wall or some people or something, you have to actually steer the other way. So if you lose your engine and you're coming around a corner, as your car coasts to a stop, you're going to have to counter steer. So that would be a slightly different free body diagram. I'll put it right over here. That would be just the normal and weight. And like I said, for this particular application, we are not going to tilt the coordinate system because we need to resolve motion and find out how much is pointed towards the center of a horizontal circle. So I'm going to do that. And that componentizes a little differently. Now we have mg downwards. We have n. Let's see now. If this is theta here, this is theta in here. So we have n cos theta up there, and this is n sine theta. So for the case of no friction necessary, we have that n cos theta equals m times g, and n sine theta equals mv squared over r. That's our centripetal force that we need. So n cos theta, that means that n can be replaced with mg over cos theta, and we can just put that into this thing and get mg sine theta over cos theta equals mv squared over r. Once again, the m's cancel, and so we wind up with g r tan theta equaling v squared. And so the speed that you can go around a corner without using any friction, any steering to get you around is this right here. That's pretty cool. Okay, if we go back to the original that has friction, we should be able to find our maximum value, our maximum speed we can go. So I'm going to go ahead and take this piece of paper and just put it over here, and we're going to do this one. Now that one, the free body diagram gets a little more complicated once we componentize it. When we componentize it, we're going to have n cos theta this way, n sine theta this way, f max cos theta this way, f max sine theta this way, and m times g. Now there are two different things we're going to learn from this. One is that n cos theta has to equal mg plus f max sine theta. Now I'm going to write out what f max is. It's mu s n sine theta Over here, for the horizontal stuff, we have that n sine theta plus f max cosine theta, and I'm going to write out f max as mu s times n cos theta equals mv squared over r. These two together are providing my centripetal force. Okay, so now we have a system of two equations and two unknowns, and we're trying to find v, and we're going to be doing it given a mu s. Yeah, let's do this with all symbols. This is fun. This is fun for me. We're going to do it with all symbols. And I don't know why I'm switching colors of pen. I think it's perfectly appropriate to stick with the red. So we need to solve one of these guys for, I think we're going to solve this side for the normal force and plug it in that side. So let's bring this term to the other side. We'll have normal times cos theta minus mu sine theta equals what's left, m times g. So that means that the normal force must be m times g over. Now I'm going to do something that I do when I'm doing algebra. Instead of writing out cos, I'm just going to put a c n theta minus mu s theta. And this is my little code that I use when I'm doing algebra for cosine and sine. If this bothers you, write out cosine and sine. I'm going to put that in over here. So we're going to have mg sine theta over cos theta minus mu sine theta plus mu cos theta. Oh, and now I'm going to write it out. Sure. Times m times g over cos theta minus mu sine theta. And that's going to equal mv squared over r. Okay. Wow. Getting exciting. So the m's all cancel. Doopa 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 doopa. We can factor out a g out of this thing. A gr if we put an r over. So we're going to have g times r. And then we're going to have, wow, we're going to have sine theta plus mu cos theta all over the common denominator of cos theta minus mu sine theta. Well, that equals v squared, so we'd have to take a square root. This is kind of, I mean, it's a lot of stuff, but it is kind of symmetric, right? There's sine plus mu cos and cos minus mu sine. We'd have to put in actual values for mu and theta to find out what the v is. Let's do that for fun, but before we do, let's think about this. What happens if mu goes to 0 if there's no friction? Well, if there's no friction, these two terms disappear and you get back what we had before. It turns into tan theta. So that makes sense. This seems to work that way. And if friction is very, very, very large, yeah, this bottom might even go negative. Depends on the theta. All right, let's put in some values that I know. 15 degrees is a pretty good bank for a racetrack, like an oval super speedway style racetrack. We said that R was 50. We know that G is 10. And we said that mu was 1. Okay, cool. Let's put those numbers in. 10, 50. Did I? Oh my God, I made a mistake. Oh my God. On the original, I made a mistake. That's pretty funny. Okay, sine 15 plus cosine 15 all over sine 15 minus, nope, cos 15 minus sine 15. And that equals v squared, so I'll have to remember to take a square root. Here we go. Sine of 15, no, what do I have to do? I have to do sine 15 plus cosine 15 equals, okay, the top is 1.22, and then I'm going to write that down right here, 1.22, and then on the bottom, cosine 15 minus sine 15 equals, and that is 0.707. And all of this is going to be multiplied by 500. So 1.22 divided by 0.707 equals and then times 500 equals, and then take a square root of that answer, and we get 29. Okay, I made a mistake back here, and I'm sure some of you caught it. I said that 10 times 50 was 50. This should really be 500. And so this isn't 7 meters per second. So let's do this. It's 22 meters per second, which is more like, what you would drive around a neighborhood, maybe up and down Los Al Boulevard. So by having a banked road, we can now drive, looks like 7 meters per second faster. So we have talked about curved roads and needing to have a centripetal force, which is being provided by friction. Then we talked about banking the corner and the fact that without friction, we can still go around the corner using this analysis where one of the components of the normal force is actually towards the center, and that with friction, although it enhances the free body diagram because friction is in a weird direction, we were able to get through the algebra and find out what's going on.